Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe, but want to be its friend.
And I'm Corinne Caputo, a writer and comedian, and friend to the universe.
Yes, and also friend to me. Hi, I'm Moiya McTier. I'm an astrophysicist and a folklorist, and I have had a complicated but mostly loving relationship with the universe for a long time. And Corinne, where are we right now?
We are in a place I've had a complicated but loving relationship with, which is the movie theater I worked at in high school. And they've really upgraded since I worked here. So now there's even more snacks, even more drinks. And guess what? Stadium seating with reclining chairs.
Oh, you're getting fancy.
And they are letting us, after we grab these snacks, they're going to let us record in this theater, and then we can go watch a movie.
Nice. Are we going to record in the projector room? I've always wanted to see a projector room.
We should just sneak in.
Yeah, let's just sneak in and then record our episode up there, and we can watch the movie at the same time.
Perfect.
Well, I don't know what movie we're going to be catching glimpses of, but I do know that we're going to be whispering up here about stellar classification schemes, which I get very excited about.
I have no idea what you just said.
I am such a fucking nerd. I'm over here like, ooh, I love schema for classifying stellar types, and other people are like, oh, you mean that sequence of letters that people use to describe stars? I'm like, yeah, that's the shit.
Yeah, that.
I really like thinking about how we classify things in astronomy, because astronomy is fundamentally an observational science, meaning we aren't running experiments on the things we study. We aren't creating our own control groups in a lab. We have to go look at stuff in space and put them into groups ourselves so that we can have large enough populations to actually do our studies on, which means we have to be good at putting things into groups of similar characteristics. So classifying is such a huge part of astronomy, but it often creates these hilarious hijinks. There are misnomers, there are bad classifications, there are beefs between different schools of astronomers who prefer one scheme over another. Like, it's fun in the way that nerds can be and have fun.
That's very sweet, and I can't wait to learn about it so I can be a part of it. But I have no idea.
Thanks, Corinne. Although I will say, you saying "that's sweet" sounded in my head a lot like, "Oh, you lovable dork."
Oh, you weirdos.
Yes, I am a lovable dork. I'll own up to it. But I do want to talk to you a bit about how we have classified stars throughout history and run by you some of the highlights of like the modern stellar types, like the big three types of stars that people think about today.
The big three.
The big three, yes. But we're going to start with historical classification schemes. And for this, like most things with the history of astronomy, we're going to go back to ancient Greece. I do want to take a moment to say that ancient Greeks did not invent astronomy. The Egyptians and the Babylonians, they were doing some very cool astronomy stuff. They were measuring the motion of stars. They were predicting eclipses. They were predicting the positions of the planets in the sky at different times of the year. So, like, older societies were doing cool astronomy, but the ancient Greeks did really ramp it up. Through a confluence of factors, they were a society that really valued learning. They also happened to be around at the right time when there were instruments and there were concepts that made it easier for people to start thinking about astronomy as a science, as opposed to some like mystical interpretation of the messages from the gods, which is what a lot of astronomy was before. So we're starting with ancient Greece. One of the first people to classify stars into different types was the ancient Greek astronomer, I guess, named Hipparchus. And now we have a telescope named after Hipparchus, and it's going around mapping stars, or at least it was mapping stars.
I love that.
It was the precursor to the really beautiful and high-achieving Gaia telescope that is mapping the Milky Way right now. But back to Hipparchus. Hipparchus in 129 BCE started labeling stars based on their brightness. So like how bright, how shiny did they appear to be. They didn't know what stars were. They didn't know what stars were made of. They didn't understand how light from a source gets dimmer as that source is farther away. Like they didn't understand any of that stuff. But Hipparchus was still taking meticulous notes about how bright all of these stars were and classifying them by their luminosity or their apparent luminosity.
Yeah, that makes sense. That's a good instinct.
Yeah, I agree, because one thing we know about stars is that they gon' shine. So why not classify them based on how much they shine?
Yes.
That's the catchphrase of today's episode. Stars, they gon' shine.
They gon' shine. That's so true. That's what they do and are famous for.
Mm-hmm. So Hipparchus made this list of stars, and he called the brightest ones that he could see first magnitude stars. Like, he was like, these are the brightest, these are the pinnacle, they are the first magnitude. And these would be stars like Spica or Sirius or even Vega. Like, those are the very bright stars. And then he put the stars into 6 groups, with the sixth group being the dimmest stars that he could see with his naked eye. And he called those 6th magnitude stars, which created this precedent for a system where a low number means a brighter star. And we have kept that system today with a little tweak.
Oh, I see.
Right,
okay.
'cause, intuitively, you would expect that the brightest star has the higher magnitude number.
Like the classic scale of 1 to 10 thing.
Exactly. Nope, we can't make it that easy.
I'm also getting so overwhelmed thinking about this. I'm like, he just had used his naked eye and looked at the sky and wrote down.
Yes.
I just feel like I've looked at the sky and I've, the longer you look, the more you might see. Like, it just feels like a task that's overwhelming.
Yeah, that's why people devoted their entire lives to doing this before there were telescopes.
Yeah.
Telescopes weren't invented until like the 1600s. So
wow.
People were looking with their naked eyes and doing really great work. Like they also didn't have the light pollution we had, so they could see a lot more stars.
Yeah.
And they would just every single night go out and take meticulous notes about where those stars looked to be in the sky.
Wow.
I know. Wild to think about.
That's a lot of work.
I could never. Like, I could not have been an astronomer 2,000 years ago.
Couldn't be me.
No, thank you. My memory is shit. Like, if I was rich enough to have paper and writing implements, great. But if I was doing it just based on memory alone, no, thank you.
No. I don't know what I would have liked to do back then, but definitely not that.
Mm-mm. No, I'm being totally honest. In today's world, given the option between sex work and astrophysics, I choose astrophysics. In that world 2,000 years ago, I'm choosing sex work every single time. Every time.
I think that it probably was an incredible job. And is.
Yeah.
And can be still.
Yeah. We're talking about sex work, not astronomy, right?
I guess it works for both. I guess astronomy can be a good job if you let it be.
But just like this podcast is coming down firmly pro-union, we're also firmly pro-sex work.
Hell yeah.
In a safe way, led by the sex workers, yes.
Yes, absolutely.
Mm-hmm. Okay, so the magnitude system.
Tell me about it.
Back to the magnitude system. So Hipparchus had this 6-group system. Flash forward like 1,700 years, and now Galileo is able to look at stars through telescopes, and he's seeing for the first time stars that are dimmer than the dimmest stars that Hipparchus saw. And we need to come up with new numbers for them. So he continued in the direction that Hipparchus went, and he was like, oh, I see a star that is too faint to see with the human eye. Let's call that magnitude 7. And it kept going that way. They also eventually started seeing stars that were brighter, so they had to go into negative numbers.
Yeah, how do you do that then?
Yeah, negative numbers.
I don't know, guys. I don't know about that. I know you put a lot of work into this.
I know.
It's the sunk cost fallacy of like, we can just start over and we're not going to lose much.
Oh my God, it totally is the sunk cost fallacy. That's exactly what's happening here. Because so young astronomers in training, like in modern day, they have to learn about the magnitude system. And I remember it being one of the more confusing concepts that I learned in an introductory astronomy class, simply because it goes backwards than how I expected it to.
Yeah.
And I know that sounds like a small thing to let get in my way, but it really made a difference. Like, I was so confused about the magnitude system for a solid semester in college.
That makes complete sense, especially if no one's being explicit with you of like, this is weird and bad.
Yes.
And like, it's not instinctual.
Yeah, just the acknowledgement that something isn't
Something's
simple
off.
and obvious,
Yeah.
that helps a lot. Okay, so Galileo, he continued this magnitude system in the 1600s, and this unstandardized chaos continued until the 1850s when a scientist named Norman Pogson.
Okay.
This is a fun name.
It's way more fun than we usually get.
Yes. Norman Pogson, he suggested, rather, I think, like with common sense, he sensically suggested that a star's magnitude should be based on its inherent flux or its inherent luminosity, its inherent brightness. Mm-hmm. And so he looked back at Hipparchus's catalog and measured the brightnesses of those stars, which we can still see, with equipment that was modern to his day in the 1850s. And he noticed that Hipparchus's first magnitude star was about 100 times brighter than the sixth magnitude star. So Pogson decided to keep that proportion where every time you go down by 5 magnitudes, you get 100 times brighter.
Okay.
Which gives us this equation called the distance modulus that I'm not going to go into here, but that means that a magnitude 5 star is 2.5 times brighter than a magnitude 6 star. So anytime you have a difference in magnitude of 1, the difference in brightness is about 2.5.
Okay.
And that works because 2.5 to the 5th power is about 100. So if you multiply 2.5 by 2.5 by 2.5 by 2.5 by 2.5, I think that's 5 of them, you get the proportion of 100 times brightness between the first magnitude and 6th magnitude star.
Okay, I get that.
Cool. So now astronomers use this magnitude system and the distance modulus, which I mentioned but will not explain, with the star Vega as a reference point. Vega is a really bright star. We say it has a magnitude of 0, and then we can scale up and down from there. So Hipparchus labeled them or classified stars by their brightness, but in the 1860s, we had this newfangled technology called a spectrograph. The spectrograph let us look at stars, take the light from them, split that light into its component wavelengths, and get a sense for what types of elements were in that star's atmosphere, with the absorption and emission lines that you would see in the spectra. They would see the absorption and emission lines, and they didn't understand what that meant back in the 1800s, but they knew that it could be used to classify these stars. They knew that it was in some way related to an inherent property of the star, so they used it to classify them. One of the first people to use spectra to classify stars was, I'm not going to assume. I was going to assume Italian, but I'm not going to assume. The scientist named Angelo Secchi, or Secchi. Let's say Secchi.
Hey, I'm Italian and I have no idea.
Sure. He took advantage of this newfangled technology and studied the spectra of stars. So the telescope would collect the light from the star, it would pass that light to the spectrograph, which would split it up into all of its wavelengths, and then a picture of that spectra would be saved on a giant photographic plate. Back then, they were made out of glass, but I've also seen plates that are made out of aluminum. One of the professors in my grad school had one of these aluminum plates turned into a table.
That's cool.
Yeah, it's like 3 feet wide. They're these giant circular dishes that, depending on what you use it for, might have different holes and different shapes in it. So the one that my professor had, that was a more modern one, and it had a bunch of holes in it where people essentially poked wires through the plate that represented the positions of different stars. So you can study these plates to see the positions of stars on the sky at different times of the year. Mm-hmm. And there are hundreds of thousands of these plates. The biggest collection of them is at the Harvard College Observatory, and there are 500,000 of these plates. Right now there's a project to digitize all of these plates called DASH, it stands for Digital Access to a Sky Century at Harvard. And they should be pretty much done digitizing most of these plates by now.
Whoa, that's so many.
I know. Well, because the sky's really big, Corinne.
Yeah, I know. This is, again, that can't be my job.
Yeah, I wouldn't have wanted this job either. But the plates that Angelo Secchi was using, instead of having the holes poked in them, the picture of the star's spectrum was essentially just like printed onto a glass plate. Because otherwise you have to look at the spectra through the telescope and then just draw it in your notebook, which, you can imagine brings in some error.
Yeah, I don't know about that. I can barely draw like a person who can draw a person, but I can't draw like an apple from memory. Well,
no, it's not from memory. You're looking at the
checking
telescope.
it as they go.
Yeah. Yeah, it's like drawing a phoenix that's sitting right in front of you, but it's still really fucking hard.
I was just reading about this woman who drew like a lot of textbook images before pictures.
Ooh.
Of course, I can't remember her name or what she did, but I thought it was like, oh, that was such an industry of like kind of drawing and relaying information via illustration when we didn't have like photos or the technology to like capture something so far away.
Mm-hmm. I think all the time about the fact that scientists used to have to be better at drawing.
Yeah.
Like there was this exhibit at one of the museums at Harvard when I was there of these beautiful botanical drawings of old flowers, and then glass recreations of these flowers based on the drawings. And when I think back to all of the naturalist drawings of things in nature, like animals and stuff, like I couldn't do that. There are so many reasons detailed. I couldn't have been a scientist 200 years ago.
Same.
Yeah, both of us, we would not be here. 300 years ago, you would not be hearing our voices.
No way.
No sirree, Bob. I haven't said that in over a decade.
I was thinking of like, when did I last hear that? That's a good one. We're bringing that back.
Bringing it back. Okay, so Angelo Secchi, after studying the spectra of these stars, split them up into 5 different classes. And it's essentially based on their color and generally what spectral features they have. So the first class is white and blue stars with really broad hydrogen absorption lines. An absorption line in a spectra looks like a black line. It looks like the absence of light because it is that the light at that wavelength has been absorbed by whatever you're observing. So an absorption line looks like a black spot, a black line, and a hydrogen line is at a certain wavelength, so they can tell what element lines they're looking at in these spectra. The second class was yellow stars with some hydrogen absorption lines and a good amount of metallic absorption lines. And remember that for an astronomer, anything heavier than helium is considered a metal. So these metallic lines would be like carbon lines and oxygen lines and nitrogen lines. The third class was orange to red stars with, and I quote, complex band spectra, which I think just means like there's a lot of junk in that star.
Yeah.
The fourth class were red stars with significant carbon bands and lines. And then the fifth class was just a catch-all. It was stars that, instead of having absorption lines, have a lot of emission lines.
Okay.
So where an absorption line looks like just like a black emptiness, an emission line would look like a bright spot. Mm-hmm. So that was in the 1860s. Like 20, 30 years later, in the late 1800s, a scientist at Harvard named Edward Pickering, whose name I don't even like saying, conducted a survey of stellar spectra with data on more than 100,000 stars. I think he had like 250 or something thousand stars that he took spectra on with these plates.
Whoa.
And the data on those plates was all analyzed by the team of women collectively known as the Harvard Computers, or Pickering's Harem. One of the leaders of these computers, these women at Harvard, was named Wilhelmina Fleming, and she classified the features of more than 10,000 stars on her own.
Whoa.
By looking at these plates, by looking at the picture of a spectra that has been printed onto these glass plates and just analyzing the features of these spectra, putting them into groups, all by eye.
I don't know. Now I'm sounding like this is a job I do want. I love little organizing tasks.
There you go. That could be nice, yeah. We now do this with very advanced computers.
Of course, I've been replaced already.
Of course. Well, back then you would have been a computer, Corinne.
Could have been me.
I know. It could have been. So we now do this with advanced computer algorithms that can look through this like forest of spectral lines and pick out the strong ones and pick out the absorption and emission lines and compare it to databases that tell you exactly what wavelength or what element you're supposed to be looking at. And we now have more data to comb through, so it's harder in that way, and we have to be more careful and more rigorous with our work. But in a lot of ways, it's so much easier to study these spectra than it was for Wilhelmina Fleming. So she took those 10,000 stars that she was classifying, that she was studying, and she split them up into more groups than Secchi had. And instead of using Roman numerals, his scheme went from 1 to 5, instead of doing that, she used letters from our alphabet, A through Q, and this was called the Draper classification scheme. Named after a man who took a picture of one of the first spectra of a star. And those classes went from A to P. There were a lot of different groups. And then there was a Q group, which was just a catch-all miscellaneous category.
Okay.
Yeah, why not? So Annie Jump Cannon is considered by most people today to be the person who came up with the modern stellar classification system. So she took Wilhelmina Fleming's Draper scheme and simplified it, taking the letters A through P and instead just going with 7 different groups, taking letters from each of those groups. So, and then rearranging them. So her scheme, which is today called the Harvard classification scheme, split stars up into 7 different groups, each assigned a letter. And those letters are O, B, A, F, G, K, and M. There are 7 of them.
Okay.
So that was in the late 1800s, very early 1900s. And then in 1943, 3 people at Yerkes Observatory in Wisconsin, and their names are W.W. Morgan, Philip Childs Keenan, and Edith Marie Kelman. So together, this new scheme is called MKK, or usually just MK because they leave out Edith Kelman. Of course, they leave out the woman. But together, these 3 decided that you should add more information to the classification scheme because the Harvard classification scheme that Annie Jump Cannon made, that only tells you about the star's spectra or its temperature.
Okay.
They also wanted additional information about the star's brightness or luminosity. So in addition to the letter, you can also have a Roman numeral that tells you basically how bright the star is within its given category.
Yeah, that makes sense.
So now we have this classification scheme from hottest to coolest, which is also brightest to dimmest, which is also shortest lived to longest lived. The stars are O, B, A, F, G, K, M.
Okay.
It's important for me to state that this is only the scheme for stars on the main sequence. So this is only the way that we can classify stars that are actively fusing hydrogen in their cores.
Okay.
Before and after they are fusing hydrogen, they're on a different path.
Okay.
And they have different words and different classifications to describe them.
Okay.
So we're only talking about the main sequence, which is stars that are burning hydrogen in their cores. I'm going to focus on 3 types of stars for the rest of the episode. The least massive stars are called M dwarfs or M types. Then in the middle, we have sun-like stars. Those are G-type stars. And then all the way at the massive end of this classification scheme, we have the O stars. Those are very hot, very bright, very blue.
Cool.
Hey friends, it's Moiya, and you know the deal. I am here to give a shout out to our amazing patrons who are supporting this podcast and keeping us going. First, I want to start off by thanking our latest pre-main sequence stars, Ashley Ellis, Jason Minich, and Leilani Lumen. Y'all are awesome. One day, you are going to glow just as bright as Rigel and Betelgeuse and all the other main sequence stars. Don't be ashamed just because you haven't started fusing helium in your cores. Next, I want to thank our latest red dwarf stars, JB and Pinky Panettiere. I'm loving all of the alliteration in this week's new patrons, so thank you so much. And as always, thank you to our sun-like stars, Sharn Llewellyn, Finn, and Ian Williams. I don't know what else to say. You're amazing, you're sun-like, you are not just stellar, you are solar. So thank you all. And you too can support us. You can hear your name on this podcast and you can make it to our patron star chart, which I made a brand new Python code to generate every single week. So you want to be on our patron star chart, and you can do all of that by supporting us on Patreon. You can find that star chart, our Patreon info, and more at our website, palebluepod.com. Or you can go right to patreon.com/palebluepod. For just $5 a month, you get access to our director's commentary /research notes for each episode, and you get to hear your name on this pod. So again, that's patreon.com/palebluepod. We will love you forever.
Shaker and Spoon is a subscription cocktail service that helps you learn how to make handcrafted cocktails right at home. Every box comes with enough ingredients to make 3 different cocktail recipes developed by world-class mixologists. All you need to do is buy 1 bottle of that month's spirit, and you have all you need to make 12 drinks at home. I feel like Shaker and Spoon is so perfect for like a dinner party or a bachelorette party, or even if you just want to be an A-plus house guest. At just $40 to $50 a month, plus the cost of the bottle, this is a super cost-effective way to enjoy craft cocktails. And you can skip or cancel boxes at any time. So invite your friends over, class up your nightcaps, or be the #1 house guest of all time with your Shaker and Spoon box. And enjoy $20 off your first box at shakerandspoon.com/palebluepod.
I love spooky things, and I love history, and I love myths and folklore that people have been using to explain the natural world from all over the globe, and I love to laugh, and I love to feel like I'm with friends. And you know what? There's just one podcast where I can go to get all of those things, and it's called Spirits. Spirits is another show on the Multitude Collective, and it's a history and comedy podcast focused on everything folklore, mythology, and the occult, but told through the lens of feminism, queerness, and modern adulthood. The 2 hosts are Julia Schaffini and her childhood best friend, Amanda McLaughlin, and together they get to learn about a different story from mythology and folklore over drinks. So the name is a pun, get it? It's spirits, like spooky stuff, but also spirits, like the stuff that'll get you crunk. So they'll cover things like the mythological origins of major franchises like Lord of the Rings and Wonder Woman, but they'll also cover modern urban legends from listeners, and they'll do a roundup of like werewolf stories from around the world. You can start listening to their more than 300 episodes that they've released over the last 6 years, wherever you get your podcasts, or by going to spiritspodcast.com. Spirits is actually one of the only podcasts that I listen to every single week when it comes out, so you can join me in listening to Spirits every single Wednesday. Again, that's Spirits, SPIRITS, podcast.com, or just go to your favorite podcast app and search Spirits. So I'll start with M dwarfs and then move up.
Yeah.
And I'll tell you just some fun facts about each of these stellar types, and then you can ask any questions or whatever you want.
I can't wait.
Okay, so first we're going to start with the M dwarfs. Astronomers have studied the mass distribution of newly formed stars. So, like, if you have a group of stars that form from a giant molecular cloud, that's what we call them, those will form, like, thousands of stars at once from a single cloud of gas.
Whoa.
Astronomers have studied those newborn clouds of stars and also like existing clouds of stars to see, is it even across all the masses, or is one type of star more common than the other? And they can explain this in an equation. That equation is called the initial mass function, and it just tells you, like, for a given stellar mass, what fraction of a new stellar population will have that mass.
Okay.
The initial mass function is another thing that really confused me when I was in my astronomy classes, because there's more than just one. Like, different scientists have made these observations and fit their own curves to them, essentially.
Okay.
And so there are different initial mass functions. Astronomers are right now still actively trying to figure out if the initial mass function in the Milky Way is the same as for the rest of the universe. Like, we don't know if the IMF is universal, or if it changes over time. Well, we think it does change over time, but we don't know how much. Another fun fact about the IMF, the most popular IMF is the Salpeter IMF. It's named after an astronomer whose last name was Salpeter. I was very good friends with his grandson in college.
Oh my God, how fun!
I know. And so I was in my astronomy classes learning about the IMF, and then later that night I was hanging out with my friends doing my homework, and I was describing to my friend what I was trying to do, and he was like, "Oh, Salpeter, that's my grandpa." And I was like, "Fuck you, Caleb. Like, you can't just casually drop the fact that I'm learning your grandfather's life work."
Was he also an astronomer?
No, not one bit.
Oh, that's so funny that you crossed paths. I love that you did.
I know. We just happened to live in the same freshman dorm, and then we're friends for most of college.
That's so cool.
I know. But according to this IMF, and according to our observations of different populations of stars, M dwarfs are by far the most common. Do you have any guess for, like, what percentage of stars in the Milky Way are M dwarfs?
Oh my gosh. My gut is to say not many because they're small, but I don't know if that's right.
Well, this isn't like what fraction of stellar mass is M dwarfs. This is just like by pure numbers.
Of all the stars?
Yeah, and I'll tell you, like, they are the most common.
60%.
Pretty close. It's somewhere between 70 and 75% of all the stars in the galaxy are these M dwarfs.
That's a lot.
And it should probably be pretty similar in the rest of the universe too, we think.
Whoa, that's really cool.
Mm-hmm. And so 75% of stars are M dwarfs, and yet I'm pretty sure we can't see any M dwarfs with our naked eye. Like, when we look out at the sky, all of the stars we can see without a telescope are more massive, brighter stars.
So most of the stars we can't see.
Yes, exactly. We are not seeing a representative sample of stars with our unaided eyes.
Yeah, wow. Okay.
Mm-hmm. So these M dwarfs, they are the lowest mass stars. They have less than 10% the size of the sun. That's both mass and radius. So they are small, they are light, they are dim, they are cool. Their temperature is less than 3,800 Kelvin. And as a comparison, our sun has a temperature of like 5-something thousand Kelvin.
Yeah, okay.
So
wow.
they're much cooler than our sun. They make up for it, though, by being very magnetically active.
I was going to say, with their sunglasses. Like, they're the coolest stars we know.
I like to think that other types of stars would boycott sunglasses because they're like,
I don't need this.
Well, that's why are you making G-type stars so special? I bet they'd feel left out.
Yeah, I buy that.
Mm-hmm. M dwarfs are very magnetically active, which has led to a lot of discussion about whether or not a planet around an M dwarf star would be a good candidate for having life.
Okay.
Because if you have a lot of magnetic activity, it might affect evolution on a world. It might affect the atmosphere of that world. Although I think most astronomers now would agree that M stars and then their slightly more massive companions, K stars, I think most astronomers would agree that that's actually the best chance for finding extraterrestrial life out in the galaxy because there are just so many of them.
Yeah.
These M dwarfs are cool. They are literally cool. Like, they have a low temperature, but they're interesting in that they transfer all of their energy from the core to the surface through convection, which we talked about in the fluid dynamics episode.
Yes, we did.
So convection, very important in the energy and heat transfer in stars, but different types of stars have different mechanisms that they use, and M dwarfs are unique in that they are completely convective with no part of their stellar body is dominated by radiation.
Ooh.
So cool. They also, in the book, in the autobiography book that I wrote, the Milky Way describes M dwarfs as the most selfish stars because they don't make heavy elements. They will make helium, and they are very good at turning hydrogen into helium, but because they're fully convective, they're also very good at like cycling or mixing that helium throughout the entire star. So they're the most efficient.
Yeah.
Yeah. So they can't start the next stage of turning helium into carbon because the temperature and pressure doesn't really get high enough to start the carbon burning. So they don't make heavy elements, and they live for a very long time. These M dwarfs can spend more than 100 billion years fusing hydrogen in their interiors.
Oh my gosh.
The universe has not been around long enough for any M dwarf to die. We have not seen this.
Oh my God.
When we talk about the end stages of an M-type star, we are basing this off of models and our understanding of physics. We have not observed this. And we never will.
That's so cool.
Because the universe is only 14 billion years old.
We're babies.
So we're babies. And these M stars are like, I'm going to be here forever.
Yeah.
So the Milky Way calls them selfish because they hoard a lot of gas for a very long time, and they don't make heavier elements that can be used in future generations of stars.
Makes sense.
After those 100 billion years, we're pretty sure that an M dwarf that has stopped fusing hydrogen in its core will just turn off. It will radiate away all of its heat from the surface of the star, and it'll get dimmer and dimmer until it is a white dwarf star. So instead of being supported by pressure from nuclear fusion in their cores, a white dwarf is supported by what we call electron degeneracy pressure, where essentially the electrons have so much energy and they're packed so tightly together that they create like a solid lattice to support the weight of the white dwarf.
Cool.
So you have this like crystalline structure that supports this almost dead and dying star.
Aw, a comfy home.
And I wanted for each of these to come up with an example of a famous member of this stellar type. And for me, when I was thinking, what's the most famous M dwarf? It was no question. For me, it has to be TRAPPIST-1. So back in early 2017, astronomers announced the discovery of a 7-planet system called TRAPPIST-1. 3 or 4 of these 7 planets are in the habitable zone of their system, meaning they are close enough. They're like the right distance from their star to have liquid water on their surfaces. Maybe. But that star that they're orbiting is an M dwarf star, about 10% the size of our sun. So they are all much closer. In fact, the entire TRAPPIST-1 system can fit well within the orbit of Earth around the sun.
Oh, whoa.
So these are tiny, but like I said before, M dwarfs are a good candidate for life out there. And the TRAPPIST-1 system was a really exciting one because there were so many habitable worlds.
I know TRAPPIST-1 because of those like kind of retro JPL posters that came out. And there's a TRAPPIST-1 that I'm looking up now, and I'll put on the Instagram when this episode comes out. But I mean, all of those posters are so fun.
I agree. I love we were kind of inspired by that for our cover art.
Yeah.
Another notable M dwarf, at least in my heart, is Kepler 186.
I think that might have a poster too.
It does. Kepler 186f absolutely has a poster.
That one, yes.
Mm-hmm. Kepler 186f is an Earth-ish sized planet in the habitable zone of this M dwarf star. I studied it in one of my projects in undergrad, and it's my favorite planet.
I love that.
Mm-hmm. And yeah, the poster is sick. I had a t-shirt of that poster, and then I grew too big for the t-shirt, so my mom put it into the t-shirt quilt she made me when I graduated college.
I love that. That's so sweet.
It was very cute. Okay, any questions about M dwarfs?
I didn't realize how many there were. I had no idea that most of the stars were this, and also that I've never really seen one with my naked eye. So.
Your eyes, when they look out at space, they are lying to you.
Yeah, they really are. It's very freaky. I'm like, what else is right in front of me that I'm not seeing?
I actually think that there's like a comforting message in here, or at least like an encouraging message. Like, you know how people always say, oh, well, the pictures that you take of the moon always look shitty, even though you know the moon is beautiful, so don't get upset about pictures you take for yourself. I feel like there's something similar here where it's like, the most common type of star isn't even visible to us. So, but we know it's there. Yeah. So like maybe something about like something that you love about yourself that isn't visible to others. It doesn't mean it's not there. Like
exactly. It just might not be visible in this moment, but that doesn't mean it's gone. Yeah, I totally agree.
People just need stronger telescopes to see the M dwarf of your personality.
Yes.
You know?
That's great.
I'm just trying to make inspirational posters here. Okay, so the next of the big three that we're going to talk about is sun-like stars, or G-type stars, if you don't want to be as solar-centric as most humans are, and most astronomers. Most astronomers would say a sun-like star. The Milky Way in the book really didn't like that. It says, call them G-type stars. Your sun isn't special. So these are, especially compared to M dwarfs, not very common in the universe. So what percentage do you think are the G-type stars?
Well, I want to think that there's a ton of them because we have one, and I'm always just like, could it be true that things are this special and rare? But I don't know. Maybe we just learned 75%. I don't think this is the full 25% remaining. But maybe like 10? Lower? 5?
Yeah, it's like 5 or 6.
Oh, wow.
So about 5 or 6% of stars in the galaxy are like our sun, which means they're pretty average in terms of everything. They're like the middle of the road for a star. So a G-type star will have a temperature between like 5,000 and 6,000 Kelvin. And I did the size and mass comparison for the M dwarfs relative to the sun. So now I just have to give you actual numbers. So the mass of the sun is 2 times 10 to the 30th power kilograms. I'm telling you it in kilograms because I cannot tell you in pounds because pounds is actually a unit of weight that is specific to Earth. It's like your mass times the acceleration due to gravity of the Earth. So since it's impossible for the sun to be sitting on the Earth, it's impossible for the sun to have a weight in pounds. But it does have a mass in kilograms. And that mass is more than 300,000 times the mass of the Earth. So
oh my God.
It's quite heavy. How many Earths do you think you could fit into the sun?
Well, I know that the sun is like if you took all the mass of our solar system, the sun is like 99%.
Yeah.
So
but I'm talking about volume, not mass.
Volume. Oh, volume. Okay.
Yeah,
okay.
how many Earths could you physically fit into the sun?
I'm
by
imagining
volume?
the sun opening up like a Pokeball.
Yes.
And like Earths are hopping in.
Yes, and you gotta catch all the Earths.
It's got to be like 1 million.
Yes.
Really?
Yes.
Not bad, not bad.
I'm so proud of
I'm
you.
kind of saying that number in like a hyperbolic way. Like it's got to be like 1 million.
Like 1 million. I know you were, but it's still accurate.
But I was right.
Yes. So it's about 1.3 million Earths
Wow.
could fit
That's a
inside
lot
the
of
sun by
Earths.
volume. Yeah, it is. And then Jupiter is in between. So you can fit like 1,000 Earths into Jupiter, and you can fit like 1,000 Jupiters into the sun.
Wow, Jupiter's so big.
And so 1,000 times 1,000 is like 1 million. Yeah. So the M star had fully convective heat transfer. The sun-like star, the G-type stars, they have a radiative core surrounded by a convective layer. And that is because the inner core's density gradient, which is like the rate at which the density changes, it's actually too steep for convection to work close to the core of a G-type star. Because convection works by a blob of material having less density than the material around it, so it rises, and the vice versa is also true. But the gradient for a G-type star is so steep that any blob of material would rise and find that it is still denser than the material immediately surrounding it, so it drops back down. So the only way that you can get heat and energy from the center of a G-type star is through radiation, so it's generating a lot of photons. And then once you get to the outer layers, the density gradient isn't as steep, so convection works. So you get convection carrying heat from like halfway to the edge of the star to the edge. If that makes sense. Yes.
Yeah, I'm picturing the lava lamp that we talked about.
Yes. So an M dwarf star, it's all lava lamp, but a G-type star, it's only a lava lamp on the outer half. A G-type star, unlike the M dwarfs, can make heavier elements, so they'll make elements like carbon and nitrogen and oxygen, but not really heavier than that. And they will fuse for about 10 billion years.
Whoa.
So our sun is 4.5 billion years old-ish. It's middle-aged.
Yeah.
We have a middle-aged sun.
Middle age is the new young.
It is, yeah. After those 10 billion years, a G-type star will puff up into a red giant. So it'll get really big, and the temperature will decrease so that it looks red. We're still trying to figure out how big the sun will get, but most estimates say it's going to eat Earth. Like the red giant phase of the sun will puff out to our orbit.
Not if we eat the sun first, Moiya. I've been saying it and saying it.
Eat the sun. Eat the sun so it doesn't eat us. So it'll puff up into the red giant, and I like to say that after it does that, it gets so hot that it starts taking off its clothes because it will start to shed the outer layers of material. So you get these beautiful nebulae, and 200 years ago or 100 years ago, astronomers thought that these nebulae that we were seeing out in space, like the beautiful, colorful clouds, they thought that that's where stars were born. That's actually where stars are dying. That is stars.
The graveyard.
Yeah, it's like how when we freeze to death, we get very warm at the end stages and we get naked. So we find a lot of frozen people naked. Stars are doing the same thing. At the end of its stages, it's going to get really warm and it's going to take off its clothes. And then we're going to find it naked because the thing left behind after that is a white dwarf, just like what the M dwarfs will become. And our sun is kind of right below the mass cutoff for an end that is more interesting than a white dwarf. So any star that is more massive than our sun probably will not end in a white dwarf. And instead they get fun nova or supernova explosions.
Nova!
Yes.
I love that word.
I'm doing a supernova dance.
The
over
supernova.
here. It's actually you can tell it's the supernova dance because I'm using my hands and I'm exploding away from my body.
Yeah, I do think of supernovas as these kind of eruption, not even an eruption, but a whiteout, in a movie when suddenly everything goes.
Yeah, a single supernova explosion in a day generates more energy than our sun will over its 10 billion year lifespan. They are
Whoa.
very bright. They are very energetic.
That's a lot of energy. Mm-hmm. Too much.
And they are able to have that much energy because they come from the most massive stars. Which brings us to blue giants like O and B type stars. I'm not going to make you guess their fraction. It's tiny. It is, according to the source that I found, and, people are still trying to constrain these measurements, but an O-type star accounts for 0.00003% of stars in the galaxy.
Oh my gosh, that is so tiny.
There really aren't a lot of these things. So an O-type star is any star that is heavier than 15 times the mass of our sun. They have temperatures higher than 40,000 degrees Kelvin. They give off really high levels of ultraviolet and gamma ray radiation. So, like dangerous radiation that our bodies wouldn't be able to handle, which is why people usually don't consider them for habitability searches. But there's another reason that people don't really consider them, and it's because they are so short-lived. An O star will fuse through all of its hydrogen in just about 10 million years, which is actually less time than it takes most planets to form.
Yeah, we have at least 10 billion behind us.
So these are very short-lived stars. The Milky Way in the book calls them they're the giving stars. They are the least selfish because they don't live very long, so they're recycling gas quickly. But they also, in their cores, can make the heavier elements all the way up to iron. And they have this fun, backwards stacking thing where by the end of an O star's life, it's not hydrogen in the middle and then iron on the outer layer. It's flipped. So that hydrogen is on the outside. Because the hydrogen gets fused into helium, gets fused into carbon, gets fused into nitrogen, then oxygen, and it goes up in the layers, just fusing heavier and heavier elements in the core until eventually the core is made of iron. And when that happens, when there is no longer fusion happening in the center, and remember from our last episode on the fundamental forces, the strong nuclear force that makes fusion happen, it doesn't operate on scales larger than the iron atom. So once you stop fusing iron, the hydrostatic equilibrium of the star breaks. This is one of my favorite phrases in astronomy, hydrostatic equilibrium. So during the main sequence stage of a star, when it's fusing in its core, the star keeps its shape because there's gravity pushing in and there is pressure from the fusion reaction pushing out. But when you stop fusing, you lose that outward pressure, so gravity can dominate and make the star implode. And that's what happens. The star implodes, but then it hits that iron core. There's so much density and much pressure and temperature that it rebounds and it explodes. And that's a supernova. Yay! So there's this supernova explosion that is so powerful and so fast that it will actually move through space at supersonic speeds, faster than the speed of light. I talked about shocks in our fluid dynamics episode. Those shocks happen because the supernova explosion, like all the outer layers of the star, they get basically shot away from the star at very high speeds. After the supernova happens, there will be a core, a remnant left of the star. And the nature of that core depends on the mass of the star that died. So if it's heavier than the sun, but less than 30-ish solar masses, then the core left over is going to be a neutron star. And neutron stars are held together by, instead of electron degeneracy pressure like a white dwarf, they are held together by neutron degeneracy pressure. These are some of the densest objects in the universe. Imagine something with the mass of our sun squeezed into, something the size of Manhattan.
Oh my gosh.
They are incredibly dense. They are so dense that the electrons on the outside of an atom get squished into the nucleus and they combine with protons to become neutrons, pretty much. So you have an entire star, an entire crystal lattice made out of neutrons.
Whoa.
So cool, so dense. And if you have a star that is heavier than 30 solar masses, the core that's left behind is the only thing denser than a neutron star. Do you have any idea what that could be, Corinne?
I don't think I know.
I think you do know. What is the densest thing?
A black hole.
A black hole.
That's what I was thinking when you were talking about how dense. I was like, wow, black hole.
Yeah, so only the most massive stars will end their lives as a black hole.
Whoa.
And then I couldn't really find any notable O-type stars because they don't live very long and there aren't a lot of them. But the star Rigel in the Orion constellation, which is just like opposite Betelgeuse, that star is a very massive B-type star, which is almost an O-type star.
Close enough.
It's close enough, yes. So those are the types of stars that can form. But that's not the entire picture because there are actually generations of stars that have slightly different properties. So the first stars in the universe were formed from primordial hydrogen and helium, like the first elements that were created after the Big Bang. Those stars would have been very bright and hot and short-lived, very similar to an O star that we would find today. And they would live for just like 10 million years or even shorter before they seeded the space between them with the elements that they fused in their cores. And then those heavier elements would get used up in the next generation of stars. And this happens over and over and over again until eventually you have stars that we see now that have heavier elements in their bodies already from the time they form. And this is, again, we started this episode with a confusingly backwards number system with magnitudes, remember? Well, we're going to end the same way because we have named these different generations of stars. And the stars that we see now that have a lot of heavy elements in them, we call them population 1 stars.
Okay.
The first stars in the universe that didn't have heavy elements in them, any elements heavier than helium, we call those population 3 stars.
Guys, come on.
I know. Which sucks. So subsequent generations of stars had more metals, and now the population 1 stars that we see are very contaminated. We actually haven't been able to find any pure population 3 stars. We think probably because they lived such short lives, but also maybe there are some left, but as they float through the galaxy, they pick up heavier elements that get incorporated into their outer layers. So maybe these population 3 stars are like hiding under their metallic trench coats.
Yeah, I love that image.
Me too. And the metallicity of a star, which is like basically the fraction of elements in that star that are heavier than helium. So a high metallicity star has like a lot of iron and stuff in it.
I don't think I've ever heard that word metallicity before.
Oh, we use it all the time.
I don't think I know it. I'm
astronomy.
like Felicity, the name, but metal.
Yeah, metallicity. It actually does affect stellar properties. And so astronomers today have to be very careful about teasing apart different factors of a star. Like, you can't just study its temperature. You have to study its temperature and its brightness and its metallicity and its you have to study all of these together. I did like a quick search for the effects of metallicity on stellar behavior. One of the cooler ones I found in my 3-minute Google search was that stars with lower metallicities, so stars that don't have a lot of heavy elements in them, they tend to spin more rapidly at the end of their lives than a high metal star.
Interesting.
And that is because stars do spin, they rotate. That rotation slows down over time. But if you have a lot of metals in your star, then you essentially slow down faster. So even if you have 2 stars that start at the same rotation speed, but one of them has a lot more metals, the the metal-rich one, which is how we say it, the metal-rich one will spin down more quickly, so it will have a slower speed at the end of its life cycle than the metal-poor star.
Ooh, cool.
That's stars.
Wow. That's a lot.
I know it was a lot. My
It's
voice.
fun.
You can probably hear how much it was in my
I
voice.
can tell.
Yeah.
I think I'm most surprised by, like I said before, how many M dwarf stars there are. And how
And
like
that we can't see them.
yeah. I think that's what's not sitting well with me.
Yeah. Oh, that's a good question. Is there anything else that's sitting uneasy with you about stars?
I like knowing the things I don't know, which obviously like can't be done, but I think I'm like, okay, I don't know a ton about astronomy, but like I hate knowing something so specific. I'm like, oh my God. Now what?
Right,
I feel like they're
yeah.
all just looking at me all the time. Can they see me?
Yes, the M stars canonically have the best vision of all of the stellar
All
types.
of them. But this is so fun, and I love thinking about how huge our sun is, and like how kind of being reminded the perfect set of circumstances have happened to lead to this.
Yeah, and I think it is. Maybe people will take some comfort knowing that we are kind of an oddity.
Yeah.
We are around a kind of rare type of star, and it's even rarer in that it doesn't have any sort of stellar companion. Most stars exist in binaries or like triplets, you know?
Twins like me.
Like Corinne, yes, our sun is unlike Corinne in that it is not a twin. but like Corinne in that, you know, for humans twins are rare. So you and the sun have that in common. Because not being a twin for a sun is rare. Good. Yeah, you're both unique. You're both special. Everyone is special.
I think it would be fun to quickly think of a mnemonic for that. Star letters, which as a reminder to everyone are OBAFGKM.
Yes. So the mnemonic that I learned in school, which I don't want other people to use, was "Oh, be a fine girl, kiss me."
Okay.
So let's not use that. Yeah. I hate it. I hate it so much. Oh, be a fine girl and kiss me. No. No. Be a fine girl and refuse to kiss me if that's what you want. Like I don't. Yeah, so we're going to come up with a couple better ones. Do you have any?
I have one.
Okay.
That I just thought of. It's very silly. It goes, "Okay, babe, all frogs gotta kick me."
They do. It's to keep their leg muscles strong.
They gotta stay strong. We need all the frogs in the room to get up and give me a kick.
Okay, babe. Okay. Mine is over by a frigid glen. Koala's mate.
I love that one. What's a glen?
Just like a cute little woodsy area.
Yeah, you're right.
Like a glen of the woods, yeah. Over by a frigid glen, koala's mate. We could do the back and forth one if you want.
Okay, here's one. Wait. Okay. Only brothers are finding... Oh, wait, I forgot the letter G. Let's go back and forth.
Okay, you want to start with only?
Only.
Bitches
are...
finding...
gold.
Gold carrots. That's with a C. That's with a C.
No, carat like 14 karat gold.
That's a C.
14K is the abbreviation. No, it's not. It's a K.
It's a K? Okay.
We won.
Yay. Gold carrots.
Mom.
Only bitches are finding gold carrots, Mom.
This isn't a phase.
Okay, can we do one more?
Yeah.
Okay, I'll start.
Okay,
I'll start. Open.
Box.
Away.
From.
Generous. Oh, I know how I want it to end.
End it.
Okay, I want it to be open box away from generous KleptoManiacs.
That's it!
I almost knocked my computer over. Yay!
Generous is so funny. If you're that's like Robin Hood, I guess. It's like stealing and giving.
And I don't know why you want to only open the box away from them, but
it's a present for them.
Oh,
they can't see it yet.
I like that, yes. Open boxes away from generous kleptomaniacs. Oh, please let us know which of these mnemonics is your new favorite.
I can't wait to hear them. You guys came up with great ones for the planets. I think these are going to be even better. And I think our movie is starting. I think we're going to see M3gan, which is what I call the movie Megan.
That's what everyone should call it.
And what everyone should.
M3gan. These were long previews.
I know. They're just getting longer these days. They're trying anything to keep you in the movie.
But I'm here for it. It worked.
But wherever you are, I hope you remember that you are space.
Bye. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.